Hello and welcome, Nord Anglia, to today's MIT Abstract on Climate Science for the Future with MIT graduate student Margaret Duffy. I'm your host, Fatima Hussein, and I'm a graduate student at MIT studying ancient Earth. Now, before we begin, I'd like to actually cue you all in to what an abstract actually is. An abstract is just a snapshot or a summary of a greater work of research or writing, and with this wonderful series, we're bringing you abstracts of inspiring MIT experts straight to your screens wherever you are around the world. So now, I am so excited to introduce you to our expert today, Margaret, who is a PhD candidate in the MIT Department of Earth, Atmospheric, and Planetary Sciences. Hi, Margaret, how are you doing?
Hi, it's so good to be here.
We are so happy to have you. So, Margaret, as someone who's a fellow student in your department, I am so excited for this presentation, and I'm going to let you go off and share your work with us.
Hi, everyone. Thank you so much for coming. I'm so excited to be talking to you all this morning. So I want to talk to you today about what I do, which is climate science. And I'm a graduate student in climate science at MIT EAPS. So EAPS stands for Earth, Atmospheric, and Planetary Sciences, and it's the same department that your host Fatima is in. And we do a lot of stuff in this department. Sometimes I say that Earth, Atmospheric, and Planetary Sciences is pretty much everything. So there's so much to talk about today. So what I'm going to do is I'm going to start by talking about climate science in general, and then just filter down a little bit into what I do specifically. So I have a picture of myself here giving a poster, and posters are actually one of the ways that scientists communicate with one another. And we do so at these big conferences, which have been put on hold for the pandemic, but I'm really excited to get back to them because it's just such a big exchange of information. I also put a picture of myself running on the slide because when I was your age, I was really into running, and I was on the cross-country team and the track team when I was in high school. And now I run half marathons and marathons. And so I thought I would show that to you guys. And I think being outside running is kind of connected to my interest in climate science. So when you think of climate science and when you think of climate, the first thing that you think of is probably climate change. One of the things about climate change that's interesting is that cherry blossoms have been blooming earlier and earlier every year in some parts of the world as a side effect of climate change or global warming. And some of you have probably experienced other effects of climate change that aren't quite so benign. And you can probably think of some of the things that are happening along with our warming climate. But I don't want to spend too much time talking about those today because I think you already know about that. And so I just want to talk about science and climate science and how we know what we know about the climate. So actually, not all climate scientists study climate change. There are lots and lots and lots of different ways to be a climate scientist, and studying climate change or global warming is just one really, really common thing. But there's lots and lots of other things to study. And so one example is paleoclimate, which is actually what your host Fatima does. And that means basically studying Earth's climate a long, long time ago. So hundreds of thousands of years ago or millions of years ago or more. And so one example of something from paleoclimate is the study of ice ages. And you've probably heard of ice ages and how if you go back a few tens of thousands of years, there was actually much more ice on Earth than there is now. Another thing is something called climate variability. And so you can study why even without human intervention, the Earth's climate is a little bit different from one year to the next. And some people even study the climates of other planets. So there's so much to do in climate science. And of course, there's the science of future climate over the next couple of decades or centuries. And that's what I do. On the other hand, if you're worried about climate change, and you care about the environment, but you're not necessarily interested in these aspects of climate science, there are actually lots and lots of different ways to incorporate climate and prioritize the environment in your career. And so I just wanted to give a couple of examples of that. So the first thing that I have listed here is environmental law, because there are lots of cases where actually lawyers have done really good things for the environment through their legal cases. Some people also are journalists, and they translate the science that scientists do into basically content that's available to everyone. Politicians are also a really big part of coming up with solutions to climate change and implementing solutions to climate change. Also, people do things like invent new technologies that are better for the environment than what we have. So there are just so many ways to incorporate climate into your career and also to study climate science. And so one of the things that I love so much about what I do is that I get to do both. I get to do science and I get to think about the climate. So here's a little schematic of all of these different aspects of the climate system that climate scientists think of. And I won't go through all of these. I just wanted to show you because there are so many things to think about. And there are people who study each of these things, each of these different aspects of climate. So there's land and ice and volcanoes and the atmosphere. And actually what I study is over here, the water cycle. And so you've probably heard of the water cycle. It's the process by which water from the oceans and rivers and from the land, what we call evaporates up into the atmosphere. And so when there's a lot of water evaporated into the atmosphere, that's what we call humid. So when you're having a really humid day, that means that there's a lot of water in the atmosphere. And then that humidity sometimes forms clouds. So as we know, clouds are made out of water vapor, and those clouds can sometimes rain out. And that's why it's a cycle, because then that rainwater goes back into the ocean and the rivers where it came from. And so that's my area. And it's actually really convenient that this schematic has the water cycle over oceans, because I specifically want to talk about some changes in the water cycle over oceans a little later in the talk. So as climate scientists, we have all of these different aspects of the Earth system to study, and we have a couple of different tools and approaches for doing so. So actually, a lot of the things that we know about climate science started as ideas on a chalkboard or on a piece of paper. And so when we do theory, we take what we know about the world, say maybe from physics or from chemistry, and we ask ourselves how we think the world should work based on what we already know. So we form these hypotheses based on previous knowledge. And then we can go out and we can test these hypotheses in a couple of different ways. A really, really big deal in climate science is observations. And there are so many different ways to take observations. Here's just one example of somebody launching a weather balloon off of a ship. And so this is a really big deal for both weather and for climate. I think maybe a little less common, but also a big factor is lab experiments. People do lab setups to study a particular aspect of the climate system in a lab setting. And then what we do is we take all of this knowledge that we've gotten from our theory and from our observations and from our lab experiments, and we put it all together in these big computer models. And that's what I'm going to spend a little more time talking about, since that's the tool that I use the most. So what we do when we make these computer models is we take that big climate system that I showed you before, and we divide up the Earth into these different cubes, and we represent the different things from this schematic that are relevant in that spot. So we zoom in on a cube and so we say, okay, what's going on here? Is it land? Is it ocean? Is it air? And we represent the things that we need to represent for that cube. And then when we run the model, the cubes basically talk to each other and move forward in time to simulate what's happening on Earth. One of the really, really useful things about these climate models is that we can change something. So if we want to know what happens if, we can study that in a climate model, which we can't do with our real Earth. And so, of course, one of the really common experiments that we do in climate models is change the greenhouse gas concentrations in order to simulate climate change or global warming over the next, say, century. And then we can see what happens based on, in this case, our own behavior. So making these climate models is a really big task, and a lot of different places have taken it on. So what I have here is a map of the world, and each dot on the map shows where there's an institution that has made one of these big climate models. And I should add that there are all different sorts of climate models, but what I'm talking about today is the most complex and the most state-of-the-art climate models. And so we have all of these different dots representing different centers and different institutions or universities or labs that have built a model. But actually, making a climate model is not a super exact science. Sometimes you have to make approximations in order to represent everything in the model the best you can, or to get it to match observations. And so the models sometimes operate a little bit differently from one another. And that's actually really useful for us as climate scientists, that each of these different dots makes a climate model that's just a little bit different, because what happens is then when we go to look at a feature, when we go to look at, say, okay, what's the temperature in Boston? Sometimes the models agree and sometimes they disagree. And so where they disagree, that tells us that we need to go back to our theory and go back to our observations and go back to our experiments and learn a little bit more about what's going on. And so I'm just going to spend just a couple of minutes talking about one example of that disagreement in my own research. And so, okay, so here's the whole globe. But if you zoom in just on the tropics and just think about rainfall over the tropics, so that's this top graph here. The tropics is 20 south to 20 north. And so what that means is that what we're looking at here is the Indian Ocean. The big basin in the middle is the Pacific Ocean. Over here is the Atlantic Ocean. This piece of land here is South America. This is Africa over here. It kind of connects on both sides. If you live in India, this is the southern tip of India here, and the Pacific Islands are here. And so what this map is showing us is one model's projection of how rainfall is going to change over tropical oceans. And so the blue is regions where this model thinks there's going to be more rain, and the bluer it is, the more and more rain the model is projecting. And then the red regions are regions where the model is predicting that there's going to be less rain with human climate change. And so I have examples from two different models, so from two of those different dots, and they look pretty different. In this model on the top, the biggest increase in rain is actually over here in the east part of the Pacific, and it's actually north of the equator, if you can imagine an equator here. In the other model, the biggest increase in rainfall is on the west side of the Pacific, and it's south of the equator. So what this is telling us is that there's something that we're not understanding. There's something that we're not quite getting right in these models, and that's causing this difference for this one particular climate feature. And so what my work did was it looked at basically why do these not agree? And so what we found is that there's a really, really close relationship between the rainfall over the ocean and the temperature right there at the surface of the ocean. So if you imagine you're out on a boat in the open ocean, what's the temperature of the water right below you? That has a really big impact actually on the rainfall. And not only do you have to get the temperature right at that location, you actually have to get the temperature right at the surrounding locations too, in order for the climate model to get rainfall accurately. And so that result makes a lot of sense to us climate scientists, because it can be really hard to get that surface temperature just right. Because if you think about it, the temperature right at the surface of the ocean is a result of things that are happening in the atmosphere above it, but also things that are happening in the ocean beneath it. And so so having this connection between rainfall and the temperature tells us that getting that temperature right is going to help us get the rainfall right. Okay, so that's what I wanted to share with you today about my own research. So I'm happy to answer any questions that you guys have about climate science, climate change, my research, or just me as a person.
That was really wonderful. Thank you so much, Margaret. That was really exciting. And there's a lot in there that I want to learn now too. So I might have to bug you with a lot of questions after this. But luckily, we have amazing questions from our Nord Anglia students on that we'll start with. So the first one, I think this was maybe inspired by your introduction and your intro slide where you talked about spending time outside and maybe how that influenced you. So one of our Nord Anglia students wants to know, what inspired you to choose studying climate science in this profession in the first place?
Yeah, that's such a great question. And I think there are a lot of reasons why people go into climate science. For me, I actually, when I was in college, when I was an undergraduate, I studied math. So I did not start out on the climate science track, and that's actually extremely common. So I was studying math, and I really wanted to do a job where I used math, but I applied it to something that mattered for people and that had some relevance to society. And so climate science was actually perfect for that, because climate change is just such a big problem and just such a big question. And there's so much to know. And I get to use what I've learned from math in my climate science all the time.
That's superb. I had no idea. So we have another question that we're going to kind of jump around all these really exciting things that you mentioned. So we have a student who's wondering, do you think that there's a way to, rescue our planet or restore the temperatures to what they're supposed to be?
Yeah, so there are a couple of different ways to think about that problem. And it's such a complicated problem because it involves not only the climate system, which is the part that I think about, but there's also lots to think about in terms of the economy and the economies of different countries. And we also have to get countries to agree. There are hundreds of countries, and they have to work together to solve this problem. And that's a really, really big challenge. So I'm going to answer this question from the perspective of a scientist and thinking about the climate system, but keep in mind that there are just so many more ways to think about this problem, and that the way that I'm answering it is not the whole story. And so what I'm going to say is that the best thing for the climate is for us to, one, stop emitting greenhouse gases into the atmosphere. We have to work together to really get our greenhouse gas emissions as low as we possibly can. And the second thing is that it would be really great to remove some of the greenhouse gases that we've put in. And so there's something called carbon capture and storage, which is not a fully developed technology. It's not perfect. We don't have really, really great practical ways of doing that yet, but doing so actually takes the greenhouse gases out of the atmosphere that we've put in and allows the climate to eventually, over a very long time, return back to its equilibrium. And so that's a really exciting area of research, is these carbon capture and storage techniques, and coming up with solutions like that. So if you're into inventing things, that's a really great idea for something that you could study going forward. There's another kind of crazy set of options, and that's what we call geoengineering. And so geoengineering is a little bit controversial, but it's a different way of tackling climate change and tackling what we've done to the climate. And unlike carbon capture and storage, where we're taking down what we've put in this case, we do something different to offset. So it's not a perfect switch back to the original climate. But what you can do, in theory, again, all of these things are great in theory, but they still need a lot of work and practice. And that's where new people come in. In theory, you can basically put little particles in the stratosphere that reflect the sunlight back out to space, or something along those lines. And that then brings the temperature back down. And that's a crazy thing, because we need the countries to agree on it, and we don't know what the consequences would be, but it could be really helpful in getting our temperatures back down if we get too far into this climate change. So there are quite a few different things that are being talked about. None of them is perfect. And so there's just so much room for new people to come along and have a career in climate change and make a really big impact.
That is totally wild to hear, these really interesting ideas for helping us mitigate the effects of climate change. So I wanted to refer back to an earlier part of your answer. So for those of us who don't know or are unfamiliar, what exactly are greenhouse gases and why are they bad in the first place?
Yeah. Thank you for asking that. I should have mentioned this earlier. So greenhouse gases are not inherently bad, but what they are is they're basically different particles that end up in the atmosphere that affect the way that the sunlight comes in through the sky. And what that does is that has an impact on our temperature, because the sun is the original source of energy for everything that we do on Earth. And so if we have these things in the atmosphere that are changing our relationship with the sun, then that changes what we feel on Earth. And so greenhouse gases modify the way that the sunlight comes in and hits the planet. And so they're not inherently bad, though. Water vapor, like I mentioned, is a greenhouse gas because it modifies that relationship with the sun. And that happens naturally. We have water in our atmosphere, even without humans putting it in there, right? That just happens. It evaporates from the ocean. And there was actually carbon dioxide, which is the most common greenhouse gas that humans are adding. There was carbon dioxide in the atmosphere before people came along and started adding it. But the problem that we're facing with climate change is that we had these nice even levels that weren't changing very much, or at least not changing very quickly. And then humans came along and started burning things for energy, right? To power our lights and everything that we do. And that changed. That meant that there was way more carbon dioxide in the atmosphere than there was before. And so that change then changes our relationship with the sunlight that's coming in. And that's the problem. That's why the Earth is changing, is that we had this nice equilibrium, what we call an equilibrium going, and we've disrupted this nice equilibrium that Earth had set up for us.
I see. So what you're saying is in order to help improve the issues that we're facing and that we're going to face, we need some of the Nord Anglia students to become inventors to restore that equilibrium. Am I getting the right message?
Inventors, scientists, politicians. Yes.
Awesome. So there's so many different things to do to help tackle this issue. So we have a really interesting question from a Nord Anglia student, and they're wondering, how has researching climate science impacted your perspective of the world?
Oh, that's so interesting. It's impacted my perspective of the world greatly. And, but I actually want to talk about an experience that I've had in which I started to experience the consequences of climate change in my own life. And that was, as I think I mentioned that I'm living in California with my family. And in California, we're having scarier and scarier wildfire seasons every year. And so even though I've been studying climate science for about 6 years now, this most recent fire season was really scary here. I don't know if any students are in California or have been to California, but it was really, really scary to have fires going on in my state. Unfortunately, none of the fires affected my own home personally, but it affected the air quality. And so I think actually seeing it happen in real time was so different from studying it. And I think now for me, there's a little bit more of an emotional connection to my work than there already was. I mean, I picked it because of its importance in the first place. And I think that this really reminded me of why it's so important and what I'm studying. And so it goes both ways. Climate science has impacted my view of the world, but also the world is experiencing climate change, and so going through the world also impacts my science.
Wow, and I think we have a really interesting question that references your marathon running and half marathon running. Okay, so they're wondering if participating in those two really amazing sports affects your studies. Does it help you in any way? Is studying climate science like running a marathon?
It is actually in some ways. I think about this a lot actually, and a lot of times when we're training for a race, runners often do what we call intervals. So it's where you run really fast for a short period of time and then you take a break, and then you run really fast again and then you take a break, and then you run really fast again and you take a break. And so sometimes when you're in school and you're studying, that can be really helpful to think about saying like, okay, I'm going to study for 45 minutes and then I'm going to take a 15-minute break. Or if you're feeling really overwhelmed by your work, going really hard and then taking a break is an interesting strategy. And so just in terms of my day-to-day life and when I'm actually sitting there working, I think actually a lot about the analogy between running and just working really in any subject or studying any subject. And then I think that there are more direct analogies also to climate, because running is actually one of the big ways in which I personally see the world. So I like to, if I'm in a new place, I like to go for a run, and I feel like I see so much of the new place through running. And a lot of the places that I like to run are trails or in nature. And that's something that is in jeopardy because of climate change. And so I think that there are just lots and lots of different ways in which there are connections between the hobby of running and climate change. And actually a lot of climate scientists, not all, but a lot of climate scientists are runners or cyclists or hikers or rock climbers and people who like to get out and see this world that we are trying to preserve.
Wow. So now our next question, I think, might tie into the idea of going hard and then taking a break. So we have a question that asks, when climate models conflict with experiment or theory or each other, how long does it take to find what's causing that conflict?
Oh my gosh, that's such a good question. And there's no one answer to that question. I'm sorry for being so vague. One of the really big problems that we've had is clouds. Clouds are really hard to get right in climate models because they're so small, right? I showed you how we zoom in on an individual box. And in the picture, those cubes looked really small, but actually in real life, those cubes are really big, so much bigger than a cloud that it's hard to figure out how to put clouds into that cube. And clouds are really important because, like I said, they're made out of water vapor, and water vapor is a greenhouse gas. And so clouds are really important for our relationship, for Earth's relationship with the sun. But it's really, really hard to get that right. So that's a problem that people have been working on for decades and decades. And actually we've made a lot of progress on it, but it's still one of the big reasons why there are differences across models. But sometimes a difference, like if you're developing a model, sometimes the difference is just like a bug in your code. I don't know how many of you have coding experience, but if you have like a typo in your code, that makes a huge difference. So if you're somebody who's actually working on making the model, you have to go through all your code. So there's different levels of the process of making a model and evaluating a model. And the different things just take different amounts of time to figure out. And clouds are sort of one of the really big ones that have been stumping us just for a really long time.
Yeah, clouds are super difficult. So I totally agree with you there. So we have a question from a student who I think might be very college minded right now. And they're wondering, why did you choose to come to MIT to study all of this?
Yes. Okay. That's such a good question. I mentioned that the name of the department that Fatima and I are in is the Department of Earth, Atmospheric and Planetary Sciences. So that's a lot of stuff. And so I chose MIT because the department that studies climate science is so broad. And so there are just so many people doing all different kinds of interesting research throughout the department. And so it's just such a good opportunity to see what geologists are doing and what planetary scientists are doing, what paleoclimate scientists are doing, while I do my future climate change work alongside them. So that was one of my really big factors for choosing MIT. Plus, it's just such a cool place to be a student. I mean, there are just so many awesome people at MIT, and just so many good ideas circulating around MIT's campus, and so many hardworking people. And so, just the combination of those things is what really drew me to MIT and what makes me really like it.
Yeah, this place is seriously special and so wonderful and so important to us. We have a question that digs into some climate theory here. How does the temperature of an area of the ocean impact the amount of rainfall that area experiences?
Yes. Okay, this is going to be just a little bit tricky to explain, but I hope that you'll try to stay with me. And there are basically, in my research, which is specific to climate change, there are two different ways that this relationship manifests itself. So one is that the temperature right there at the surface has an impact on what we call the buoyancy. And so that the buoyancy is basically, if you think about the air that's right there near the surface where we are, the buoyancy is the tendency for that air to want to rise. So if you have really buoyant air, it tends to want to go up in the atmosphere. And that's when you get clouds and rainfall. But if you have not very buoyant air, it tends to not want to go up and just stay there. And then we tend to not get clouds and rainfall when we have not buoyant air. And we can also have downward motion, and that also doesn't really create rain. So a really warm region tends to increase the buoyancy of the air and cause rainfall in that way. But I mentioned specifically actually the patterns and how we have to not only get that original temperature at that one spot right, we also have to get the temperature in the surrounding regions right. And the way that works is that if you have a really warm spot and then a really cold spot right next to it, that impacts actually the pressure of the air. So the atmosphere is actually pushing down on us because of gravity. And there are little differences. There are little differences in just how much that happens. And that's proportional or related to the temperature. And so if you have these different differences in pressure because of the temperature, then you can get winds across the temperature, what we call the temperature gradient. And those winds, then you end up, if you have winds that are coming toward one another, then the air at the surface has nowhere to go but up. And so, like I said, that upward motion then tends to be associated with rainfall, clouds and rainfall. And so that's the relationship. Hopefully that was somewhat clear. So both the temperature locally right at that point, and then also understanding the gradients and the whole pattern.
And the student who asked that question can continue to study the hydrological cycle, for example, to dig into those nitty-gritty details for sure.
Yeah.
We have a really, really excellent question from a student who's wondering, how does deforestation affect all of this? Does that affect the amount of water in the air or anything?
Yeah, that's right. That's such a good question. And you're right. And I think I'm going to actually just say more broadly that the way that humans use land has an impact on the climate. And so part of it is through moisture. And the moisture can then have an impact on the temperature and the rainfall. And so yeah, you're right. Changing the way that we use the land can change the climate in that region, or the way that area impacts our climate. And so that's one of the really big things that we have to put into models is how the land is used in different regions. And so we have something called an urban heat island effect, where if you have a really urban area with lots of concrete, it actually tends to be warmer than other areas. So that's kind of an interesting example of another way in which humans are impacting the climate.
Wow. And students wondering about the technology involved in all of this. So you are using these computer models that can get pretty complicated. And I assume that requires a lot of computing power. So this student is wondering, how has the course of studying climate change actually advanced or changed because of technology. And when we get better technology, does studying climate get harder?
Does studying climate get harder? No, it gets better. That's such a such a great question, because that's actually one of the really big things that we talk about in climate science is staying on top of all the latest technology and making sure that we're using it in the best ways and to get our climate models just right. And so the other thing is that climate models are very similar to weather models, and so weather forecasts have improved. And you all are probably maybe too young to know, but you could ask some grown-ups about how the weather forecasts have improved over their lifetime. And actually, a lot of those improvements are due to the computer. And I'm going to just be a little bit more specific here and talk about one of the ways in which improving the computer technology can improve our climate models. If you remember from my slide where I had the cubes that I mentioned that we use for our climate model, the smaller those cubes are, the more those cubes that we have, the better able we are to represent the climate. And because all the things that we're trying to represent happen on different scales. So the smaller the cube is, the more processes we can get in there. And so we've been able to make those cubes smaller and smaller because of improvements in computing. And that's been a really big help to studying, to climate modeling, and also to weather modeling. So that's one of the ways in which improvements in technology can really help us. And I'll also say that these computer models, the really big climate models that I've been talking about, use a ton of computing power. You cannot run it on your little desktop at home. You have to use what we call supercomputers. And so that's part of why. So all those different dots that have a different model, they often have these big supercomputer centers. They're computers that take up like whole rooms, and we use those to run our climate models. So it's pretty exciting, pretty interesting.
Wow, that is so cool. So we have a student who's wondering about the past. So they've aptly identified that humans haven't been around too long, but climate has been changing regardless. So how do we know what climate was like back in the day?
Oh my gosh, I'm not a paleoclimate person, and actually your host Fatima could answer this better than I could. I will just say that I think it's amazing what paleoclimate scientists do. I was floored. I had that same question when I started. And it's just like, how could we possibly know all of these things about what happened before? And so I'll just give you an example of what people do, how people figure this out. And what they can do is they can cut into a tree, for example, and then look at the different rings. So if you slice open a tree, which you shouldn't try at home, but if you slice open a tree, you can see there are these different rings associated with how long the tree's been around. So you can tell like what the climate was like from for the whole lifetime of the tree based on the rings. If you take that cross section, and another kind of bigger example of that goes back even further is that you can do a similar kind of thing actually with ice. So if you go to a region where there's been ice for like a really long time, like at the Arctic, you can drill down and pull out a vertical section of ice, and you can learn things about what the climate was like a long time ago through these ice cores. So rocks, trees, ice, all sorts of things that people study and then figure out what it means for the climate from before. But I'm not doing a great job of describing this because this isn't quite what I do. Fatima could do a better job. My biggest takeaway point here is that it's amazing.
I agree. I think you did a fine job explaining it, and that there's so many hints in the nature we have access to today that tells us about the past. So that is super exciting. And one day I hope to work with one of those ice cores. That would be super duper cool. So we have a question from a student who's wondering how we incorporate weather data into our climate models. So you mentioned that meteorology is getting more accurate because we have better technology. How do you take, tomorrow's temperature and consider that in line with your climate models?
Yes, that is a great question. So let me just talk a little bit about the relationship between weather and climate. And let me just talk a little bit about the difference between weather and climate, which I think it sounds like at least the person who asked the question, and probably a lot of you know. But so weather is like the day to day, right? So you wake up and what's the weather going to be like today? climate doesn't worry about what it's going to be like on this given day. Climate worries about like the averages and the highs and the lows for the whole year, for the whole decade. And so it doesn't, the climate models don't worry about getting, what's the weather going to be like on July 26th, 2034, right? The climate right. But the climate model worries about making sure that the summer temperatures are right. So the climate is what some people say climate is what you expect and weather is what you get. And that's an interesting way to think about it. Another way to think about it is that your climate produces kind of a bag from which you can grab your days of weather. And then the weather kind of reaches into the bag and picks out a day. And there are differences from day to day. And so weather models and climate models are very similar, but of course, weather models are really interested in actually getting the forecast right for, say, tomorrow. And climate models don't worry that much about getting the exact day right. And so you can run the climate model out for a really long time, whereas the weather model, you want to do what we call data assimilation. And that's where we take these observations. I think I showed a picture of somebody launching a weather balloon. You take the observations and you put it into your model and use that to kind of tune your model or refine your model and make it better. And so the way that weather models and climate models worry about the short-term processes and getting the exact weather right is the really big difference. But they do tend to improve, as you mentioned, I would say kind of in parallel or simultaneously, because they're so similar, a lot of the technological improvements do apply to both.
Got it. And when you're creating a climate model or analyzing the results of one, are you thinking about things like sea level rise, which we know is happening, is going to continue to happen, and things like volcanoes going off, for example?
Yes, those are such good examples of things that climate scientists think about. So if you remember from my little schematic, I'm over there studying the water cycle, but there are lots of people who study volcanoes, and that's relevant to both the future climate and also paleoclimate and just understanding what's happened in the past. Because volcanoes actually, they emit these aerosols that also change our relationship with the sun. And so they have a really big impact on climate. And so, that's such a good example because that's so important. Understanding whether a volcano went off is just so important to understanding the past climate. And sea level rise, that's another really, really, really big topic in climate change and understanding why the sea level rises and where it rises, by how much, and what the impacts of that are really, really important subjects in climate science.
Now, based on these really excellent questions we've had, I get the sense that we have a lot of people on this call who are going to engage and work with climate in the future. Maybe some of them will be climate scientists, maybe some of them will be policymakers. But let's focus on the climate scientists, since that is your expertise in what you do. What are some of the good qualities that climate scientists, these young climate scientists, can cultivate for the future?
Yes, if you are interested in climate and having a career in climate, which I think is such a great idea, it's just such an impactful area. I would say the best thing that you could do is pay attention in all of your classes, not just your science classes. And I know that that's probably not what you want to hear, but when I was your age and when I was in school, there were so many moments where I'm sitting in class and I'm like, when am I ever going to use this? And I have to say, as a climate scientist, I use pretty much all of it. You can really imagine that I'm using the things from my math, physics, and computer science classes for the reasons that we mentioned. But actually, writing is really, really important. And in my opinion, your scientific ideas are only as good as your ability to communicate them. And so paying attention to your I shouldn't say English, but your language classes and your writing classes, that's really important. Also, of course, climate is really intertwined with policy and the economy. So paying attention in your history classes and your government classes and your economics classes can really tell us a lot about some of the solutions to climate change and some of the things that people talk about when they talk about solving climate change.
Got it. So you heard it here, folks, from Margaret. Pay attention in every single one of your classes. You will.
It's all useful.
And now, Margaret, unfortunately, we have to begin our closing, but this has been so exciting. And I think that a lot of these students are going to continue to think about these really important ideas and our shared, future with relation to climate in the future. So I wanted to thank you sincerely for joining us all the way from California. We hope you and your family stay safe with another summer hot season coming up. So we really appreciate your time and your expertise, and thank you for inspiring all these wonderful Nord Anglia students who asked some really stunning questions today. I am
amazing.
So
amazing. Thank you all so much for coming and for listening to me talk. This has been awesome. And thank you so much, Fatima, for hosting.
Oh, of course. It's totally a pleasure. And I'd like to also thank, before we close, the MIT Nord Anglia collaboration for making this entire series possible. MIT Abstracts is a real pleasure, and we look forward to the future ones. Thank you again, Margaret.